Hello there. Welcome to the Deep Sleep Science channel. The night is quiet. The air is still. Somewhere above you, beyond the thin veil of the atmosphere, billions of suns are shining all at once. Their light weaves together into something so vast, so delicate, that it looks like a faint cloud stretching across the sky. We call it the Milky Way, but that name hardly captures what it truly is. It is not just a stripe of light, it is home. We live inside a galaxy so immense that no single human mind can hold it entirely at once. When you look up at that pale band on a moonless night, you are looking through thousands of light years of space. Every grain of brightness you see is not dust, not vapor, but the combined light of distant stars. Some are newborns, still wrapped in the dust of their birth clouds. Others are ancient, dim embers nearing their end. Between them drifts a sea of gas and dust, the raw material of creation. And somewhere, within one quiet spiral arm, a small yellow star burns steadily. Around it spins a blue planet. And on that planet, in a small corner of a larger world, sits you, listening, breathing, part of the Milky Way listening to itself. It can be hard to imagine that everything you've ever known, every forest, every city, every thought exists within one thin slice of a single spiral arm. The galaxy is 100,000 light years wide, but our sun lies only about 26,000 light years from the center, orbiting peacefully in a lane of quiet called the Orion Spur. If you could travel outward from Earth at the speed of light, the fastest speed possible, it would take 26,000 years to reach the heart of our galaxy. That's how enormous our home truly is. Yet, despite its size, the Milky Way is not chaotic. It is exquisitely structured, the result of billions of years of balance between two great forces: gravity, which draws things together, and angular momentum, which keeps them spinning apart. Those two forces have been in conversation since the universe began. Their dialogue is written in stars. To understand the Milky Way, we must begin at the beginning, at the moment when the universe itself was still young, quiet, and almost empty. 13.5 billion years ago, not long after the Big Bang, space was filled with a thin fog of hydrogen and helium. There were no stars yet, no galaxies, no light, only potential. Then, slowly, gravity began its patient work. Tiny ripples in the density of that cosmic fog became slightly denser over time. Like water collecting into droplets, gas gathered into the first clouds. Within those clouds, pressure built, and the first stars ignited, brilliant, enormous, short-lived suns that burned through their fuel in a few million years. Those first stars were made only of the simplest elements, hydrogen and helium. But through the pressure of fusion, they began to build new ones: carbon, oxygen, nitrogen, iron. And when they died, they exploded, scattering those heavy elements into space. Each generation of stars made the next one richer. The Milky Way was born from these enrichments, from the ashes of older, smaller systems that merged together. Astronomers believe our galaxy began as several tiny proto-galaxies, small collections of stars and gas slowly merging under mutual gravity. Each collision created new waves of star formation, heating gas, stirring dust, and building the structure that would one day become our familiar spiral. The earliest stars of the Milky Way were unlike any we see today. They were massive and pure, burning with blue-white brilliance and dying in cataclysmic supernovae. Their remnants, neutron stars, black holes, and heavy elements seeded the surrounding space with material that would form later generations of stars, planets, and, eventually, life. For billions of years, the Milky Way grew by consuming smaller galaxies. Even now, it continues this slow feast. If you could look with infrared eyes, you'd see faint rivers of stars, tidal streams, stretching across the halo of our galaxy. These are the torn remains of smaller galaxies that ventured too close and were pulled apart by gravity. One such system, the Sagittarius dwarf galaxy, is currently being absorbed, its stars wrapping around us like silk threads. In this way, the Milky Way is a living thing. It grows. It changes. It remembers. The spiral pattern we see today is not a static form frozen in time. It's a wave, a dance of density that moves through the galactic disk. Stars themselves drift in and out of those arms. The arms are simply regions where the material is temporarily compressed, a traffic jam of stars, gas, and dust moving in rhythm. The Milky Way's rotation gives it shape. The center bulges with old, red stars, dense, ancient, and stable, while the arms, thin and glowing, cradle younger, bluer stars born from clouds of gas. If you could look from above, you'd see it as a glowing whirlpool, its arms coiling gently like waves frozen in time. And all of it, every star, every world, every drifting atom, is bound together by the invisible hand of gravity. Gravity does not rush, it whispers. It is patient. It's the reason our sun circles the galaxy without flying away. It's the reason gas clouds collapse into stars, and stars collapse into black holes. It's the quiet force that sculpts the universe. But gravity alone can't explain everything we see. When astronomers measured how fast the Milky Way spins, they found something strange. The outer stars were moving too quickly, as if an unseen mass were holding them in place. That's how we discovered dark matter, the invisible scaffolding of the cosmos. Dark matter doesn't shine, doesn't reflect, doesn't interact with light. But it does have mass, and mass means gravity. It surrounds the Milky Way in a vast halo that extends far beyond the visible stars. Without it, our galaxy would fly apart. With it, the spiral holds. This halo of dark matter is like a ghost structure, a hidden hand shaping everything we see. Its presence tells us that most of the matter in the universe is not the kind we know. Not atoms, not molecules, not the stuff that makes you or me. We live in a universe where the majority of matter is invisible, silent, and unknown. And yet, through its gravity, that invisible matter has drawn the visible universe into being. So the next time you look at the Milky Way's soft shimmer, remember, most of what's holding it together can't be seen at all. But what we can see, the light, the structure, the glowing arms, is breathtaking. Our galaxy is 100,000 light years across, yet only about 1,000 light years thick. That's thinner, proportionally, than a sheet of paper compared to its width. If it were a dinner plate, our solar system would be a speck of dust near the edge. Above and below that thin disk stretches the galactic halo, a sphere of ancient stars and clusters orbiting far beyond the arms. These globular clusters, tight swarms of hundreds of thousands of stars, are among the oldest objects in existence. They formed when the galaxy was young, before the spiral pattern had even emerged. Their stars are ancient and metal-poor, their light steady and red. The halo is like the Milky Way's memory, the place where the oldest stories are kept. Every globular cluster is a page written in starlight, telling us about the galaxy's youth, how fast it spun, how it formed, how it gathered mass from the dark. And so, from that quiet fog of the early universe to the graceful spiral that now fills our sky, the Milky Way has evolved, patient, luminous, and alive with motion. Everything you know, the sun, the earth, the air you breathe, was shaped by its gravity, its chemistry, its long, slow dance. At the very center of the Milky Way lies a mystery, quiet, patient, and immeasurably powerful. It is not a star, not a cluster, but something far stranger, a supermassive black hole, known to us as Sagittarius A star. Hidden behind thick clouds of gas and dust, it sits about 26,000 light-years away at the galaxy's gravitational heart. We cannot see it directly, but we can see what it does. Our galaxy has already merged with many smaller systems, and in the far future, it will merge with its neighbor, the Andromeda Galaxy. That collision, 5 billion years from now, will tear apart and reform both galaxies into a new elliptical giant. Even then, the stars themselves will rarely collide. The space between them is too vast. But their combined gravity will weave a new cosmic structure, a new home for the descendants of our Milky Way. For now, though, our galaxy spins in graceful balance, a structure both fragile and enduring, shaped by forces that act slowly but relentlessly. Its spiral arms shimmer with youth, its core glows with age. It is a masterpiece painted not in color, but in time. When you look up and see the faint milky glow stretched across the night, you are looking into the architecture of infinity, a design that has been evolving for billions of years, written in gravity, drawn in light. Every journey through the Milky Way must, eventually, turn inward to the small corner we call home. Amid all the galaxy's grandeur, the spiraling arms, the star clusters, the dense heart glowing at its center, our solar system drifts quietly through the thin mist of a minor spiral spur. It is neither central nor exceptional. Yet from here, we can see the whole orchestra of the galaxy, playing around us in slow motion. Our sun lies about 26,000 light-years from the galactic center, near the inner edge of a modest region called the Orion Spur, a small bridge of stars connecting two major spiral arms, the Sagittarius arm and the Perseus arm. This spur is a tranquil neighborhood by galactic standards, not as crowded as the inner arms, but rich enough to host bright star clusters, nebulae, and regions of gentle star formation. It's the ideal environment for stability, a quiet backwater of the Milky Way where life could have time to arise and evolve. Our sun is a second-generation star, born about 4.6 billion years ago from a collapsing cloud of gas and dust enriched by older, dying stars. Since its birth, it has been orbiting the Milky Way center at roughly 230 kilometers per second, completing one full circuit every 225 million years, a galactic year. That means, in its lifetime, the solar system has made about 20 orbits around the galactic core. In that time, continents have shifted, species have come and gone, mountains have risen and eroded, and civilizations have appeared and vanished, all while the sun has quietly continued its endless journey. This motion is not a perfect circle. The solar system moves in a slightly elliptical path, bobbing gently up and down through the galactic plane every 30 million years or so. When we rise above the plane, the night sky would look subtly different, the Milky Way's band appearing thinner, the dust less obscuring. When we dip below, the view thickens again, stars crowding together like a shining river. This vertical motion may even affect life on Earth. Some scientists have proposed that periodic mass extinctions might coincide with the solar system's passage through denser regions of the galaxy, where increased comet activity or radiation could influence our planet. Whether or not that is true, the idea reminds us that even life's rhythms on Earth may be linked to the larger cycles of the Milky Way. The Sun is one of about 200 billion stars in the Milky Way, and it belongs to a quiet, middle-aged community. Nearby lie other suns, most faint, some binary, some small red dwarfs barely visible even through telescopes. Our nearest stellar neighbor, Proxima Centauri, lies just over 4 light-years away. In cosmic terms, that's practically next door. Yet if the Sun were a basketball, Proxima Centauri would be a small marble located 7,000 kilometers away, the distance from New York to Beijing. The space between stars is truly immense. The Sun's closest neighbors form a small local collection known as the local bubble, a region of low-density gas carved out long ago by multiple supernovae. Within this bubble lie about 1,000 stars within a radius of a few dozen light-years. Many are red dwarfs, cool, dim, and long-lived, the silent majority of the galaxy. Others, like Sirius, Altair, and Vega, burn brighter, young, and energetic. Despite the distances, all these stars share a common motion. They orbit the galactic center together, each following its own path, but bound by the same gravitational symphony. To an observer from afar, our Sun would be just one more dot moving in harmony through the great spiral. Before the Sun existed, there was only a cloud, a drifting region of gas within one of the Milky Way's spiral arms. Nearby, massive stars lived and died, enriching that cloud with heavy elements. When one of those stars exploded as a supernova, its shockwave rippled through the gas, triggering collapse. From that collapse, our Sun ignited. The leftover material flattened into a spinning disk from which the planets eventually formed. Every rock, every ocean, every atom of your body originated in that ancient collapse. The solar system is, in a sense, a recycled fragment of the Milky Way's ongoing experiment with matter. The Sun itself is an ordinary G-type main sequence star, stable, yellow, and middle-aged. It fuses hydrogen into helium in its core, converting 600 million tons of matter into energy every second. Yet even at that rate, it has enough fuel to shine for another 5 billion years. During its long journey through the galaxy, the Sun has passed through different environments, dense molecular clouds, quiet interarm regions, and regions filled with cosmic dust. Each environment leaves its mark, subtly shaping the solar system's magnetic field and the path of cosmic rays reaching Earth. Not every region of the Milky Way is friendly to life. Near the galactic center, intense radiation and frequent supernovae make survival difficult. Farther out, the density of stars drops, and heavy elements, necessary for rocky planets, become scarce. Between these extremes lies a band known as the galactic habitable zone, a region where conditions are stable enough for complex chemistry and where metals are abundant enough to form terrestrial planets. Our Sun sits comfortably within this zone. It's a remarkable coincidence, one that may explain why life arose here. Too close to the core, and radiation might sterilize worlds. Too far out, and there might not be enough material to build them. Here, in the middle, the balance is just right. This doesn't mean Earth is unique. There may be billions of other planets within the Milky Way's habitable zone, worlds with oceans, clouds, and perhaps even their own versions of life. Each one would be a reflection of the same galactic processes that shaped us: gravity, chemistry, time. From our tiny planet, it's easy to forget how immense the Milky Way truly is. When we look up at the night sky, every visible star we can see, thousands of them, lies within a few thousand light years. That's just a fraction of the galaxy's full width. Most of the Milky Way is invisible to us, hidden by dust or distance. Yet, through radio, infrared, and X-ray telescopes, we can see farther than our eyes ever could. We can map the spiral arms, trace the rotation curve, measure the chemical composition of distant regions, and even detect the faint whispers of hydrogen at the galaxy's edge. From our small corner, we have come to understand the entire structure that holds us. When we send spacecraft beyond our solar system, like Voyager 1 and Voyager 2, they carry messages for anyone or anything that might someday find them. Each golden record on board includes a map showing the sun's position relative to nearby pulsars, a cosmic address pointing back to our home. Those spacecraft are now more than 20 billion kilometers away, still moving outward, still carrying the story of one small world in the Milky Way. Someday, they will drift among the stars, silent ambassadors of Earth, and perhaps, in millions of years, cross into another star's neighborhood. Even then, they will still be within the Milky Way, still part of the galaxy's slow, endless flow. Our sun will not remain forever in the Orion Spur. The spiral arms themselves move, and the sun will eventually pass into a new region, perhaps into a denser arm, where star formation is higher, or into a quiet gap between arms. Each transition will bring new skies, new neighbors, and new cosmic weather. Far in the future, when humanity's descendants, or whatever beings come after us, look up from some other world orbiting this same sun, they will see a different night. The constellations we know will have drifted apart. The familiar patterns will be gone. But the Milky Way's glow will still stretch across the heavens, a reminder that we are part of something ancient and vast. The sun will continue its orbit, unhurried and steady, for billions of years more. It will see the Milky Way merge with Andromeda, the stars rearrange, and the galaxy's shape transform. By then, Earth may be gone, but the atoms that once made it, and us, will still be here, scattered through the galactic wind, part of new stars and new worlds. We may be small, but we belong to something eternal. Every life, every breath, every thought ever born on this planet is a ripple in the Milky Way story, a brief spark within its shining arms. When you stand beneath the night sky and see that pale ribbon stretching from horizon to horizon, you are seeing your home from the inside. You are standing within the galaxy, looking through its body, surrounded by its light. The Milky Way is not something above you. It is around you. It is within you. And it carries you through the cosmos, as it has carried countless generations of stars before. The Milky Way, vast and glowing, is not only a landscape of stars, it is a timeline. Every shining point you see belongs to an age, a moment in the galaxy's immense biography. Some stars are ancient beyond imagination, formed when the universe was young and heavy elements were rare. Others are new, still wrapped in the dust of their birth clouds. All of them together, old, young, and unborn, make up the galaxy's living memory. When astronomers look across the Milky Way, they see not a single population of stars, but several distinct generations. These are not families in the human sense, but lineages defined by their chemistry, their motion, and their place in time. Each generation holds clues to the galaxy's history, to how it grew from a chaotic cloud into the orderly spiral we inhabit today. The oldest generation, known as Population 2 stars, were born when the universe had just begun to cool from the fire of the Big Bang. They formed from gas made almost entirely of hydrogen and helium, the only elements the young cosmos had to offer. In those first stars, fusion built heavier elements for the first time: carbon, oxygen, silicon, iron. When those stars died in supernovae, they scattered their newly forged matter into space. That material became the foundation for the next generation, stars like our Sun. Population 2 stars are ancient and faint, glowing with the soft red of age. Most dwell in the Milky Way's halo and bulge, orbiting in long, looping paths that cross the galactic plane. They move in all directions, not confined to the orderly rotation of the spiral arms. Their random motions are fossils of the Milky Way's turbulent youth, a time when smaller galaxies merged to form the structure we see today. Astronomers find these stars by their metallicity, the measure of heavy elements in their composition. Population 2 stars have almost none, their atmospheres nearly pure. They are, in a sense, made of the universe's original ingredients. To study them is to look back more than 10 billion years into the earliest era of galactic formation. Then came the younger generation, the Population 1 stars, rich in heavy elements, bright and colorful. Our Sun belongs to this family. These stars are found mainly in the spiral arms, born from gas and dust enriched by countless earlier supernovae. Their higher metallicity makes them fertile ground for planets, moons, and complex chemistry. The Milky Way's beauty, its glittering arms, its glowing nebulae, owes much to these stars. Between the ancient and the modern lies a bridge, the intermediate stars that formed when the galaxy was settling into its spiral shape. These mid-age suns populate the thick disk, a region older and more elevated than the thin, star-forming layer below. They serve as a record of the transition from chaos to order, from a rough early halo to the smooth, rotating disk that defines the Milky Way today. The thick disk tells a story of upheaval. Billions of years ago, when the Milky Way was still young, it collided with a smaller galaxy, one now called Gaia Enceladus. The merger shook the Milky Way structure, scattering stars into new orbits and thickening the disk. Many of those displaced stars still travel above and below the plane, silent witnesses to a long-forgotten cosmic impact. Even now, astronomers can trace their paths through space, using data from satellites like Gaia, which measures the positions and motions of more than 1 billion stars. From that data, patterns emerge: waves, ripples, and scars left by ancient collisions. It's as though the galaxy itself carries memories written in motion. Each generation of stars enriches the next. When massive stars die, they return their matter to the interstellar medium, heavy elements that later form new stars, planets, and life. The cycle repeats endlessly, each turn of the spiral mixing and refining the material of the Milky Way. In this way, the galaxy is not static but evolutionary, its chemistry changing over time like a growing organism. If you could take a cross-section of the Milky Way and read it as a geologist reads rock layers, you'd see epochs of enrichment marked by supernovae and starbursts. The center would be older, richer, more complex. The outer regions would be simpler, younger, more pristine. Even light itself carries this story. The subtle fingerprints of elements imprinted in starlight reveal when and where each star was born. To look at the stars, then, is to look through time. The oldest among them began shining before the Milky Way had even taken its current shape. Their light has been traveling ever since, carrying the memory of the universe's first structures. When that light reaches us, it brings whispers from an era before Earth existed, before the sun, before any life at all. And the youngest stars, glowing bright blue in the spiral arms, are the promise of the galaxy's future. They are short-lived but vital. Their lives fuel the evolution of everything else. In a few million years, they will explode, scattering their elements outward and enriching the medium once again. Their ashes will one day become part of new clouds, new stars, and perhaps new worlds. In this way, the Milky Way sustains itself. It is a system of renewal, not decay. Even death here serves creation. The galaxy's beauty lies in this quiet continuity, in the way every end becomes a beginning. There is a deep poetry in the thought that the iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was forged in long-dead stars. The Milky Way has been writing us, atom by atom, for billions of years. And we, in turn, are one way it has learned to see itself. Somewhere out there, beyond the solar system, are stars that formed at the same time as our sun, siblings born from the same cloud. Over billions of years, they drifted away, scattered through the spiral arms. Astronomers have found a few, tracing their motion backward through space like detectives following faint trails. Each discovery is a reunion across time. Fragments of a single stellar nursery now spread across light years of emptiness. Such stories remind us that the Milky Way is not just a structure of stars, but a family of origins. Every atom, every orbit, every glimmer of light is connected through shared ancestry. What appears as distance is, in truth, continuity spread thin across space. The galaxy's diversity, its red giants and blue dwarfs, its quiet suns and violent supernovae, all stem from the same process, the slow enrichment of matter through time. Each new generation adds complexity to the next, and with it, the possibility of greater structure, from dust to stars, from stars to planets, from planets to life. That is how the Milky Way grows, not merely in size, but in intricacy. Each cycle brings more potential for creation, more room for awareness. And so, though its stars burn out and its arms shift, the galaxy evolves toward depth, toward meaning. When we measure the metallicity of stars, we are measuring history. When we map their orbits, we are tracing memory. When we look at their light, we are reading the autobiography of the Milky Way written in its own language of fire. To stand beneath the night sky and look up at that pale band of light is to see this story all at once, a biography unfolding in silence. The older stars speak softly in red and gold. The younger ones shine blue and white, fresh with energy. Together, they are the voice of the galaxy itself, whispering across time. I am old. I am young. I am becoming. Within the grand spiral of the Milky Way, stars are rarely born alone. They come into existence in groups, communities of light emerging together from the same cloud of dust and gas. For a brief time, they share a common home, bound by gravity and proximity, before the slow drift of time pulls them apart. These gatherings, the star clusters and associations, are the galaxy's families. Each one is a page in the story of how the Milky Way renews itself. A single molecular cloud, cold and dark, can give birth to hundreds or even thousands of stars. As gravity pulls the gas inward, it fragments into dense knots. Each knot collapses into a protostar, glowing faintly in infrared as it gathers mass. Around these young stars, disks of dust begin to spin, the seeds of future planets. Within a few million years, the cluster emerges from its cocoon, its members shining brightly in ultraviolet and blue light. These clusters are dazzling sights, though few live long enough to stay together. The smallest ones dissolve within tens of millions of years, their stars scattering into the galactic field. But while they last, they illuminate the spiral arms like sparks frozen in motion. The open clusters are the Milky Way's youth, loose, bright gatherings of hundreds or thousands of stars, spread across a few dozen light years. They are the products of recent star formation, found mostly in the spiral arms where gas is plentiful. One of the most famous is the Pleiades, also called the Seven Sisters, a cluster visible to the naked eye in the constellation Taurus. Though we see only a handful of stars, it contains more than 1,000. The Pleiades are only about 100 million years old, mere infants by galactic standards. Surrounding them is a faint veil of blue reflection nebula, the remnants of the dust from which they formed. Clusters like the Pleiades are laboratories of stellar evolution. Within them, astronomers can study stars of nearly identical age and composition but different masses, watching how those differences shape their brightness, color, and fate. Open clusters are the classrooms where we learn how stars live. But time is unkind to such gatherings. As the cluster orbits the galaxy, tidal forces, the gravitational pull of nearby clouds, stars, and spiral arm patterns slowly tear it apart. Members drift away, their shared motion preserved only faintly. After a few 100 million years, the cluster dissolves completely, its stars becoming part of the wider galactic population. Even so, these long-lost siblings can sometimes be found again. With precise measurements of position and motion, astronomers have identified stellar streams, groups of stars that still move together after billions of years apart. They are the ghosts of ancient clusters, still traveling side by side through the galaxy's vast sea. Our own sun likely began life in such a cluster, a gathering of hundreds of stars born from the same nebula. Over time, those siblings dispersed, carried by the spiral arms. Somewhere in the Milky Way, they are still shining, each following its own orbit, each carrying the same chemical fingerprint of origin. When we look for them, we are looking for our cosmic relatives, suns born under the same dawn as ours. If open clusters are the galaxy's youth, then globular clusters are its elders, immense, ancient spheres of stars that orbit far from the galactic plane. Each globular cluster contains hundreds of thousands, sometimes millions, of stars bound tightly by gravity. They are nearly as old as the Milky Way itself, more than 12 billion years in age. Seen through a telescope, a globular cluster looks like a jeweled sphere, a dense, radiant core surrounded by a faint halo of stars. The famous Omega Centauri in the southern sky contains so many stars that its gravity makes it slightly flattened, more like a miniature galaxy than a cluster. These clusters live in the halo, far above and below the galactic disk. They move on long, looping orbits, passing through the plane only occasionally. Their stars are mostly population II, ancient, metal-poor, and stable. They formed at a time when the Milky Way was still gathering its shape, perhaps even before it became a spiral. Some globular clusters may not have been born here at all. Evidence suggests that many were captured from smaller galaxies the Milky Way devoured long ago. Their unusual compositions hint at origins beyond our own. They are the immigrants of the galactic halo, carrying stories from worlds long vanished. Within their crowded cores, stars are packed so tightly that they sometimes collide or merge, forming blue stragglers, anomalously young-looking stars created by the union of older ones. These rare objects defy the normal rules of stellar evolution, glowing hot and blue amid the aged red population. They are the rejuvenated few, stars that found new life in the dense company of their peers. Globular clusters have remained stable for billions of years, outlasting empires of stars, yet even they are not eternal. Gradually, tidal forces strip stars from their edges, leaving faint trails that stretch into space. Over immense timescales, even these ancient structures will dissolve, their stars joining the great galactic chorus. Between the tight order of clusters and the solitude of field stars lies another kind of family, stellar associations. These are very young groups, loose gatherings of hot, massive stars that have only recently emerged from their birth clouds. Their gravitational bonds are weak, and within a few million years they disperse completely. Such associations often form in regions like the Orion-OB complex, where enormous molecular clouds give birth to waves of massive stars. These stars shine fiercely, flooding their surroundings with ultraviolet light that carves cavities in the gas. Their winds and radiation compress nearby clouds, triggering further star formation, a domino effect of creation across light years. In these associations, we see the galaxy's most intense energy at work. The massive blue O-type stars live only a few million years before ending in supernovae, enriching the region with heavy elements and reshaping the surrounding medium. Though short-lived, their impact lasts for ages, influencing the chemistry and structure of the spiral arms. All of these clusters and associations trace back to the same origin, the vast molecular clouds drifting through the spiral arms. These clouds are the wombs of the galaxy, cold and immense, stretching for hundreds of light years. Within them, pressure waves from passing spiral arms or supernova explosions trigger collapse, leading to the formation of clusters. As these clusters evolve and disperse, their stars migrate throughout the Milky Way. The galaxy's stellar population is thus a continuous mix, the remnants of countless generations of clusters, each contributing its members to the whole. When astronomers map the positions and motions of stars, they find subtle streams and patterns, the lingering traces of clusters long gone. The galaxy, it seems, never forgets. Its memory is written not just in light, but in motion. Every star in the Milky Way follows its own orbit around the center, shaped by gravity and influenced by its neighbors. Some paths are nearly circular. Others are elongated ellipses that carry the stars far from the plane before returning again. In this dance, clusters serve as temporary harmonies, chords that sound briefly before dispersing into the larger symphony. Over billions of years, this movement mixes the galaxy's populations. Stars from one arm may drift into another. Halo stars pass through the disk, and gas from the outer regions spirals inward. The Milky Way is not a static structure, but a vast circulation, a living system where everything is in motion, where every particle, every photon, participates in the same eternal flow. The clusters and associations remind us that nothing in the galaxy lasts forever, yet nothing truly disappears. Each star that leaves its birthplace carries the memory of that place in its composition and motion. Even when the cluster is gone, its influence remains, diffused but enduring, like perfume lingering after the flower has withered. So too with us. We are the scattered remnants of a cosmic family, atoms once bound together in the hearts of stars, now dispersed across space and time. We may be brief, but we belong to an unbroken lineage that began long before humanity and will continue long after. The Milky Way's families of light, open, globular, and fleeting, are its heartbeat. Through them, the galaxy remembers how to create, how to grow, and how to endure. Each new generation carries forward the chemistry of the last, weaving an unending tapestry of renewal. In the dark silence between the stars, this continuity hums softly, like a pulse in the void. Every star we see is part of that pulse, a flicker in the vast, breathing body of the Milky Way. The farther you move from the Milky Way's bright disk, the thinner the starlight becomes. The great river of the spiral arms fades, and the space between stars grows vast and silent. Yet even here, in the dim outskirts, the galaxy continues. It extends far beyond the glow we can see, wrapped in an enormous, invisible sphere of ancient stars, dark matter, and gas. This is the halo, the Milky Way's faint, forgotten crown. It is easy to imagine the halo as empty, but it is not. Scattered through it are hundreds of globular clusters, each a dense swarm of old stars orbiting like lanterns around a mountain. Between them drift solitary suns, survivors of long-vanished galaxies, their paths looping high above the plane before plunging back through it again. These are the Milky Way's elders, older than the spiral itself, formed when the universe was still learning how to build. Their orbits are not smooth or circular. They travel in long, inclined ellipses, some stretching tens of thousands of light years from the center. As they move, they weave together into a sphere of slow motion, like fireflies drifting in a dark cathedral. Each one carries the chemical signature of its birth, tiny amounts of heavy elements forged before the galaxy was rich. By reading that chemistry, astronomers can trace which stars were born here and which came from beyond. Because the halo is so diffuse, its stars seldom meet. Centuries or millennia can pass between encounters. Yet the halo is not static. It is filled with subtle streams, rivers of stars drawn out from smaller galaxies that once orbited too close. These tidal streams wrap around the Milky Way like faint ribbons. Some form loops, others stretch endlessly outward into the void. They are the fingerprints of gravity at work, evidence of the galaxy's slow, patient cannibalism. One of the largest of these is the stream from the Sagittarius dwarf galaxy, still in the process of being torn apart. Its stars trace a looping path that crosses the sky from the southern to the northern hemisphere, a glowing scar only visible through careful measurement. Every few 100 million years, more of its mass is pulled away, joining the Milky Way's outskirts. What was once a separate island of stars becomes another thread in the larger whole. The halo also holds traces of even older mergers, events so ancient that their remnants are spread across the entire sky. The Gaia satellite has revealed vast structures, the debris of galaxies swallowed billions of years ago. Among them is Gaia Enceladus, whose collision with the young Milky Way reshaped the entire disk, heating it, thickening it, and seeding it with stars. We live amid the echoes of that encounter. Our own sun orbits through a galaxy built from many ancestors. Beyond the visible halo lies the unseen. Dark matter, the mysterious substance that outweighs all the stars combined, forms an enormous cocoon around the Milky Way. We cannot see it, but its gravity shapes everything we do see. It determines the speed of rotation, the stability of the spiral, the bending of light from distant quasars. Without it, the galaxy would fly apart. With it, the Milky Way holds together like a single organism bound by invisible bones. Astronomers map this darkness indirectly, measuring how fast stars move at different distances from the center. They find that even far from the bright disk, the orbital speeds remain high, defying expectations. The only explanation is mass we cannot see. Simulations show that this dark halo extends hundreds of thousands of light years, perhaps to halfway toward Andromeda. It contains most of the Milky Way's true weight, a silent foundation older than any star. The halo is not entirely cold. It holds thin gas, hot from ancient shocks, glowing faintly in X-rays. This gas connects the galaxy to intergalactic space. Through it, material flows inward and outward, some falling toward the disk, some escaping forever. The Milky Way breathes through this halo, exchanging matter with the wider universe. It is the boundary where our galaxy ends and the cosmic web begins. Out here, the view would be astonishing. From a star in the outer halo, the Milky Way would appear as a delicate whirlpool suspended in darkness, a luminous spiral stretching across the black. The arms would shimmer faintly, wrapped around the golden core, while beyond them the universe would unfold in silence, distant galaxies scattered like sparks on velvet. It is a view no human has ever seen directly, but we can imagine it, our home seen from the outside, fragile and magnificent. The halo also serves as the galaxy's archive. Its ancient stars preserve the earliest chemistry of the cosmos. By studying their spectra, scientists can reconstruct how the first generations of stars enriched the universe. Some of these halo stars contain traces of elements that existed before heavy metals were common: barium, europium, strontium, products of the first supernovae. They are living fossils, each one a record of creation written in light. Among the halo's most mysterious inhabitants are the high-velocity stars, objects moving so fast they can escape the galaxy entirely. Some are remnants of binary systems disrupted when one member became a supernova. Others may have been flung outward by the immense gravity near the central black hole. They carry with them fragments of the inner galaxy, streaking into intergalactic space like sparks from a forge. Even as they depart, they remain part of the Milky Way's story, expanding its reach into the void. The halo's emptiness belies its importance. It is the mediator between the Milky Way and its neighbors. Streams of gas connect us to the Magellanic Clouds, two smaller galaxies orbiting nearby. Their interactions send tides of material flowing toward the Milky Way, forming structures like the Magellanic Stream, a vast ribbon of hydrogen stretching across the southern sky. These inflows feed the galaxy, replenishing the gas needed for new stars. The halo is not just a remnant of the past, it is the source of the future. Even the shape of the halo is not perfectly round. Subtle asymmetries reveal that it is being tugged, twisted by encounters, and by the motion of the dark matter itself. The Milky Way, though seemingly steady, is constantly flexing under these cosmic tides. Every interaction leaves a faint vibration that echoes for billions of years. The halo listens and records. If we could accelerate time, we would see the halo shimmer like a living veil. Streams would weave and merge, globular clusters would drift like slow comets, and waves of gas would ripple outward from the disk. The entire structure would breathe, expanding slightly, contracting, pulsing with the rhythms of star formation and gravity. From the outside, the Milky Way would seem almost alive. All the while, light from its core travels outward, crossing this immense halo before escaping into the wider universe. That light carries within it the sum of all that has happened, the births, the deaths, the collisions and quiet ages of calm. To an observer far away, our galaxy appears as a single point of brightness, flickering faintly among billions. Yet within that point is everything. The halo's old stars, the spiral's young suns, the dust, the gas, and the stories of countless worlds. When we study the halo, we are peering into our galaxy's past and its structure beyond sight. We learn that the Milky Way is both luminous and invisible, both solid and ghostly. It is a cathedral built of stars, surrounded by the whisper of things unseen. The halo may be faint, but without it the galaxy would not exist as we know it. It is the quiet frame around the portrait, the unseen line that holds the art together. And when the Milky Way and Andromeda finally merge in the far future, it is the halos that will touch first. Long before their disks collide, their dark matter halos will begin to overlap, blending their gravities. The dance of union will start not with light, but with shadow. Slowly, imperceptibly, the two galaxies will feel each other's pull, and the halo will become the bridge between them. In that distant age, new streams will form, new clusters will be born, and the halo will grow ever wider. The stars that now drift alone will find themselves part of a larger whole. Even in collision, there is creation. Even in endings, there are beginnings. The halo teaches this quietly, stretching its arms around the galaxy like time itself. From Earth, we cannot see this realm directly. We sense it through mathematics, through light curves, through the delicate gravity it exerts on what we can observe. Yet its presence surrounds us. Every orbit the sun makes, every motion of every star, is shaped by it. The halo is the invisible sky behind the sky, the unseen presence that makes the Milky Way whole. The invisible halo that surrounds the Milky Way holds more than just relics of the past. It governs the galaxy's present. Within its gravitational grip, the spiral disk turns, the stars orbit, and the gas flows. Every motion within the Milky Way is a consequence of this vast, unseen structure, a cosmic skeleton made not of atoms, but of mystery. The dark matter halo is both a prison and a protector, holding the galaxy together while allowing it to move through space like a single, breathing being. It is strange to think that the stars we see, all the glowing arms, the bright core, the clusters and nebulae, account for only a small fraction of the Milky Way's true mass. Most of what exists here cannot be seen. It does not emit light or reflect it, yet it outweighs everything visible by 5 to 1. This dark matter does not interact with the light we know, but it shapes the paths of photons through gravity alone. In this way, it reveals itself only indirectly, as a sculptor whose hands never touch, but whose work fills the cosmos. The Milky Way's spiral pattern, so graceful and persistent, owes its stability to this dark halo. Without it, the combined pull of all the visible stars would not be enough to maintain the spiral arms for billions of years. The galaxy would wind up like a coiled spring, its structure lost to entropy. Instead, the hidden mass acts as an anchor, slowing the rotation just enough to sustain balance. Through it, the galaxy achieves order, a delicate equilibrium between the light of stars and the weight of the unseen. Around the Milky Way orbit dozens of smaller companions, the dwarf galaxies that trace faint paths through the halo. Some are bright enough to be seen through modest telescopes. Others are almost invisible, composed mostly of dark matter themselves. They are like moths drawn to a flame, their paths elliptical and slow, each one feeling the deep gravity of the central spiral. The largest of these companions are the large and small Magellanic Clouds, luminous smudges visible from the southern hemisphere, drifting through the night as reminders that even galaxies have satellites. These two dwarf galaxies are bound to the Milky Way by an ancient gravitational tie. They orbit not as perfect circles, but as spiraling paths, leaving long trails of gas and stars behind them. Together, they form an ongoing dialogue of matter, the exchange of hydrogen, dust, and momentum. Their gravitational pull distorts the Milky Way's outer disk, bending it slightly into a warp that undulates above and below the plane. To us on Earth, this curvature is invisible, but radio telescopes reveal it clearly. The Milky Way's edges lift like wings. The Magellanic Clouds are not passive companions. Their approach has stirred waves of motion within the Milky Way's halo. The gas that streams from them, known as the Magellanic Stream, wraps around the galaxy in an enormous ribbon more than 600,000 light-years long. This stream glows faintly in ultraviolet light, a whisper of ongoing connection between galaxies. It represents both loss and renewal, for the gas drawn away from the clouds will one day feed new generations of stars within the Milky Way's arms. Gravity has a patience that no living thing can match. It works slowly, invisibly, weaving the motions of galaxies into an endless choreography. The Milky Way's smaller companions orbit for billions of years, their paths decaying so gradually that it seems almost static to us. Yet over cosmic time, they fall closer, their material merging with ours. Some have already vanished entirely, absorbed into the halo and the thick disk. Their stars still move among us, indistinguishable from native-born ones, yet each carries a distinct chemical accent, a fingerprint of foreign origin. The Gaia mission has allowed astronomers to identify some of these ancient immigrants. By mapping the orbits and compositions of millions of stars, it reveals which ones belong to long-vanished galaxies. We now know that much of the Milky Way's inner halo was once part of a single large system that collided with us about 10 billion years ago. The event transformed our galaxy, thickened its disk, and stirred its motions into complexity. Without those mergers, the Milky Way would be smaller, simpler, perhaps less capable of birthing so many worlds. The dwarf galaxies that remain today are fragile but tenacious. Their shapes are distorted by our gravity, stretched into ellipses or shredded into streams. Yet they continue to orbit, like memory fragments circling the mind of a dreamer. Each one adds to the richness of the Milky Way's halo, bringing in new stars, new gas, and new stories. One day, they too will vanish, and their remnants will join the spiral, indistinguishable from all the rest. The interplay between the Milky Way and its satellites is not one-sided. As our galaxy pulls on them, they in turn tug on us. The gravitational dialogue between them sends ripples through the disk, waves that can trigger bursts of star formation or warp the outer arms. These disturbances travel slowly, taking hundreds of millions of years to complete a single oscillation. Through them, the galaxy's surface vibrates like a plucked string, its resonance lasting long after the original touch has passed. Beneath this grand motion, the dark matter halo continues its quiet work. It extends far beyond the last visible star, merging eventually with the intergalactic medium. Its particles, if they can even be called that, may drift through everything, even through our bodies, without leaving a trace. They are ghosts of matter, fundamental yet elusive. Scientists have built elaborate detectors deep underground, hoping to catch the faintest hint of interaction, but so far, the dark matter remains silent. It is a presence that defines the universe by what it withholds. Still, its effects are unmistakable. The rotation of the Milky Way defies Newton's expectations. The outer regions move too fast for the visible mass to explain. Only by including the unseen halo does the model fit reality. It is as though we live inside a vast, invisible ocean, unaware of the water that carries us. The stars, the planets, the nebulae, all are just islands on the surface of this hidden sea. If one could see dark matter, the view would be extraordinary. The halo would appear not as a smooth sphere, but as a web of filaments, tangled and intricate, glowing faintly with energy. Within those threads, galaxies like ours would hang like dewdrops, each one connected to others through gravity's invisible architecture. The Milky Way is not isolated but part of this larger cosmic network, a single node in a vast, living lattice that binds the universe together. At the scale of the local group, our Milky Way and the Andromeda Galaxy are the two dominant masses, each with its own halo extending far into intergalactic space. Between them lies a bridge of dark matter and faint gas, the gravitational midpoint of their shared domain. Over the next several billion years, they will drift closer, pulled by mutual attraction, until they finally merge. Even now, their halos are already touching, overlapping in a quiet embrace that precedes the coming collision. From this slow interaction arise subtle effects. Both galaxies may experience faint tidal pulls that alter their rotation, shift their satellites, and rearrange their outer structures. The Magellanic Clouds, too, feel these distant influences, their orbits slightly altered by the combined gravity of both giants. The local group is a cosmic family bound not just by space, but by an interlocking web of motion. Nothing within it moves alone. Every orbit affects every other. Though we will not witness the full merging of the Milky Way and Andromeda, the first stages have already begun. Small perturbations in stellar motion, minor shifts in gas streams, and faint distortions in the outer halo are the earliest whispers of that destiny. The collision will not be violent in the human sense. Stars are too far apart to collide directly, but the gravitational chaos will reshape both galaxies entirely. In their place will arise a new, larger system, perhaps a smooth elliptical galaxy glowing softly against the black. Long before that future comes, the Milky Way will continue to live its present rhythm, orbiting, breathing, evolving. The dark matter will hold it steady, the satellites will circle, and the spiral arms will continue to spin like luminous spokes in an unseen wheel. Everything that happens here, from the birth of a star to the fall of a comet, occurs within that balance. We are all part of the same gravitational whisper, participants in a story that began before the first light and will continue after the last. The understanding of this invisible framework does not diminish the wonder of the stars we see. Instead, it deepens it. To know that the night sky is only the visible portion of a much greater whole is to realize that mystery is not an absence of knowledge, but its horizon. The Milky Way's glow, magnificent as it is only the surface of a truth that surrounds us, silent, immense, and waiting to be understood. And so, we look upward, sensing the presence of what cannot be seen, feeling the pull of the unseen sea in which we float. The galaxy turns, the halo endures, and through it all, light and shadow remain entwined, forever shaping the story of our cosmic home. At the heart of the Milky Way, where the spiral arms converge and the density of stars grows 1,000-fold, lies a region unlike any other. It is a place of extremes, where gravity, energy, and time interweave in ways that defy easy description. The galactic center is both the oldest and most restless part of our home, a cosmic furnace that has burned since the galaxy's birth and continues to shape its destiny. The journey inward begins gradually. As we move toward the center, the familiar patterns of the spiral arms tighten. The gas becomes richer, the star clusters denser, and the radiation more intense. Here, in the inner few thousand light years, orbits begin to twist under the pull of the central mass. The stars no longer follow the smooth paths seen in the outer disk. They move in complex, looping trajectories, responding to the immense gravity well at the core. This region is known as the bulge, a vast, rounded structure of older stars that rises above and below the plane like a glowing lantern. It contains hundreds of billions of suns, most of them ancient, their light softened by dust and distance. Through optical telescopes, much of the bulge is hidden behind veils of interstellar material, but in infrared light it shines clearly, a golden sphere beating at the heart of the Milky Way. The bulge is not smooth. It is shaped like a bar, slightly elongated, as though the galaxy's center were twisting in slow motion. This bar acts as a cosmic conveyor, channeling gas from the spiral arms inward toward the nucleus. Over millions of years, that flow feeds the dense clouds and clusters near the very center, sustaining cycles of star formation and fueling the hunger of something far greater, the black hole that resides at the Milky Way's core. There, hidden behind billions of stars and thick curtains of dust, lies a region only a few light hours wide. It cannot be seen directly in visible light, but its presence reveals itself through motion. Stars near the center race at incredible speeds, some moving at thousands of kilometers per second, whipping around an invisible point that emits no light. The only possible explanation is a supermassive black hole, an object millions of times the mass of the Sun, yet compressed into a space smaller than the orbit of Mercury. Astronomers have named it Sagittarius A*, after the constellation in which it lies. Though black holes themselves emit no light, the space around them glows with energy. Gas drawn inward forms a hot, swirling disk that radiates in radio waves, infrared, and X-rays. Occasionally, the black hole flares, sending bursts of radiation outward as matter spirals past the event horizon. Each flare is a reminder that, though silent most of the time, the heart of the Milky Way still beats with cosmic fire. This black hole is not an anomaly. Nearly every large galaxy harbors one at its core, as though such objects are necessary organs of galactic life. The relationship between galaxies and their central black holes is intimate and mysterious. The more massive the galaxy, the heavier its black hole tends to be. It is as if both grew together, the galaxy feeding its heart, the heart regulating the flow of energy and matter through the system. In the Milky Way's case, Sagittarius A* is relatively quiet. It accretes matter slowly, its hunger modest compared to the voracious black holes in active galaxies. Yet evidence shows that in the past, it may have been far more active. Faint traces of enormous bubbles of high-energy gas, stretching tens of thousands of light-years above and below the disk, hint at an ancient outburst. These Fermi bubbles, as they are called, glow in gamma rays, remnants of a time when the central black hole released a colossal jet of energy, sculpting the surrounding space. Even now, the region near the core remains turbulent. The density of stars is so great that close encounters are common. Clusters of young, massive stars orbit dangerously near the black hole, their lives brief but intense. These stars, some of the most luminous in the galaxy, formed in an environment where gravity is stretched to its limits. Their existence raises a question that continues to puzzle astronomers. How can stars form in a region where tidal forces should tear their birth clouds apart? The answer seems to be that the very processes that make the center violent also compress the gas to the point where creation becomes inevitable. Destruction and birth coexist, feeding each other endlessly. Closer still to the black hole, within a light year, lie stars that orbit with astonishing precision. Using infrared telescopes, scientists have tracked their motion for decades, watching them complete full ellipses around the unseen mass. These orbits have provided the most direct proof, yet that the core contains a black hole of about 4 million solar masses. No other explanation fits the data. Each star is a messenger, moving in obedience to the invisible geometry of space-time itself. Time near Sagittarius A* flows differently. The deeper one falls into its gravity well, the slower time passes relative to the rest of the galaxy. Were we able to hover safely near its edge, we would see the universe beyond speed up, while our own clocks would tick languidly. From a distance, any object falling toward the black hole would seem to freeze just above the event horizon, its light stretched and dimmed until it vanished. Yet from the object's perspective, the fall would continue inexorably inward, across the boundary beyond which no return is possible. Though this region is far beyond human reach, it is not beyond imagination. We understand it through mathematics, through the equations of general relativity that describe how mass warps the fabric of space and time. The black hole is not a hole in the traditional sense, but a distortion, a curvature so steep that all paths lead inward. Within it, space and time trade places. Direction becomes destiny, and all futures converge to a single point. It is humbling to know that at the center of our galaxy lies such a paradox, a place where physics itself is tested to the edge of comprehension. Yet without this singularity, the Milky Way might never have formed as it did. The black hole's gravity influences the orbits of millions of stars, maintaining order in the chaos. It anchors the bulge, regulates the inflow of gas, and perhaps even drives the spiral pattern through subtle gravitational feedback. The galaxy's heart is both destroyer and creator, shaping the conditions for everything that orbits it. Around this central region, gas clouds swirl in intricate patterns, glowing in radio and infrared light. Supernova remnants mingle with dense molecular filaments. Shock waves ripple through the medium like ripples across a pond. The area is alive with energy. Magnetic fields twist and reconnect. Cosmic rays surge, and high-speed winds blow outward from the core. Yet amid this turbulence, there are pockets of calm where stars continue to form, proving that even in the most extreme environments, life finds a way to organize itself. From Earth, the galactic center is hidden behind a curtain of dust, but radio telescopes pierce that veil. The images they produce are not of light we can see, but of signals translated into color, the glow of hydrogen atoms, the pulse of magnetic fields, the whisper of synchrotron radiation spiraling from electrons moving near the speed of light. Together, they reveal a landscape of unimaginable scale, arcs of plasma, rings of gas, and the faint flicker of Sagittarius A** at the center, a dark eye surrounded by fire. In the quiet of the night, when we look toward the constellation Sagittarius, we face this core, though we cannot perceive it with our eyes. The stars we see in that direction are only the nearest layer of a vast, hidden structure. Beyond them, 26,000 light-years away, the black hole waits, patient and eternal. Its gravity extends through every atom of the Milky Way, binding us invisibly to its destiny. Perhaps it is fitting that the heart of our galaxy is dark. In that darkness lies the balance of all things, the reminder that creation and collapse are not opposites, but parts of the same cycle. The stars that orbit there burn bright for a time, then fade, their matter drawn inward to begin again. The galaxy turns, and its heart remains, silent and constant, the axis upon which all else revolves. If the Milky Way could speak, perhaps it would describe this heart not as a void, but as memory, the memory of its birth, the point from which everything else unfolded. Around it, stars dance in slow, elegant loops, light bends and curves, and time itself takes on a shape. In that center, unseen yet felt by all, lies the essence of what the galaxy is: unity, balance, and the endless rhythm of existence. Surrounding the heart of the Milky Way lies a region of intense creativity, a broad, luminous ring where gas and dust gather to give birth to new stars. After the gravity and violence of the central black hole, this zone feels almost like a rebirth, the place where destruction transforms into renewal. Astronomers call it the central molecular ring, and it is among the most active nurseries in the galaxy, a great circular storm of matter perpetually shaping and reshaping itself into light. This ring encircles the core at a distance of several hundred light-years, thick with molecular clouds denser than almost anywhere else in the galaxy. Within these clouds, gravity works quietly, drawing atoms together, compressing hydrogen until it glows. In the infrared, this region is a tapestry of glowing filaments and knots, where each point of brightness marks a stellar womb. Though invisible to human eyes, the ring radiates powerfully in millimeter and radio wavelengths, whispering the story of creation in frequencies far beyond our hearing. The process here is ceaseless. Gas flows inward along the galactic bar, spiraling toward the center until it meets the dense molecular ring. There, it stalls and piles up, compressed by shock fronts and magnetic fields. The material grows unstable, fragments, and collapses into clusters of newborn stars. These clusters illuminate the dust around them, creating shells and bubbles that expand into neighboring regions, triggering more star formation. It is a chain reaction of creation, a galactic heartbeat pulsing with each new generation of light. The young stars born in this ring are massive and short-lived. They burn with fierce blue-white light, their energy pouring into the surrounding clouds. Their winds carve cavities, their radiation strips electrons from atoms, and their eventual deaths scatter heavy elements into space. In just a few million years, these massive stars live entire lifetimes, enriching their environment with the elements that will one day form planets and life. Around them orbit smaller, longer-lived stars, quiet embers that will continue to glow long after the giants are gone. Everywhere in this region, opposites coexist. Heat and cold, density and emptiness, destruction and creation, all balance each other like breath in the galaxy's lungs. The molecular ring is turbulent, yet it follows a rhythm set by gravity and rotation. Gas enters, forms stars, and is expelled again in winds and explosions, only to cool, fall back, and begin the cycle anew. In this balance lies the secret of the Milky Way's endurance, its ability to renew itself endlessly, transforming chaos into structure again and again. From the perspective of deep radio telescopes, the molecular ring appears as a swirling band of carbon monoxide and other molecules, orbiting at hundreds of kilometers per second. Supernova remnants glow faintly within it, their shock waves rippling through the gas. Regions like SGR-B2 and SGR-C shine as immense radio sources, their dense cores hiding some of the most active star-forming complexes known. In these places, the birth rate of stars rivals that of entire dwarf galaxies. The scale defies comprehension. Each cloud could contain enough material to make millions of suns. And yet, despite its grandeur, the ring is transient on cosmic timescales. The gas that fuels it will be consumed or dispersed within tens of millions of years, and new material from farther out in the galaxy will drift inward to take its place. The molecular ring is less a fixed structure than a moving wave of renewal, forever reconstituting itself from the debris of earlier generations. The galaxy lives through these circulations, like an organism whose cells are constantly replaced, but whose identity endures. From this ring outward, the density of stars gradually decreases, and the structured spiral of the Milky Way begins to take shape again. Here, the galaxy's great arms unfurl like luminous ribbons, each one a corridor of dust, gas, and starlight. The spiral arms are not rigid entities, but patterns, waves of density that move through the disk, compressing matter and sparking star formation as they go. The gas enters the arm, collapses into stars, and exits on the other side, leaving a trail of newborn suns in its wake. These spiral arms are the Milky Way's most striking feature, visible even from within as a river of light crossing the night sky. From above, they would appear as elegant curves, their tips winding slowly outward from the center. The pattern is not fixed. It shifts and evolves, driven by the combined gravity of billions of stars and the dark halo beyond. Yet to us, it feels eternal, a signature written into the structure of space itself. Each arm hosts countless stellar nurseries similar to those of the molecular ring, though spread over much larger regions. Nebulae like the Eagle, the Lagoon, and the Trifid are all part of this grand chain of creation. Their luminous forms are merely local expressions of the same process that sustains the galaxy as a whole, the conversion of gas into light, of potential into radiance. As the spiral pattern sweeps through the disk, it leaves behind a wake of young clusters, associations, and star streams. These are the seeds of future generations, drifting gradually outward, blending into the field of older stars. The Milky Way's arms thus act as both factories and highways, producing and dispersing stars in a continuous cycle that maintains the galaxy's vitality. The rotation of the Milky Way is not uniform. The inner regions move faster than the outer ones, yet the spiral arms persist as standing waves, their pattern speed slightly slower than the star's orbital motion. This resonance creates zones of stability, regions where gas accumulates and stars linger longer than elsewhere. Such zones often coincide with enhanced star formation, producing rings and spurs that give the Milky Way its intricate, layered structure. In these details, the galaxy's artistry reveals itself. It is not a static form, but a dynamic harmony of motion. Within the disk, the interplay of forces is delicate. Gravity draws matter inward. Centrifugal motion pushes it outward. Magnetic fields weave through the gas like invisible threads, and supernova explosions inject turbulence and heat. These competing influences prevent collapse while enabling renewal. Without them, the Milky Way would quickly exhaust its resources. With them, it endures in a state of near-perfect balance, teetering between order and chaos, stability and transformation. Embedded within the spiral arms are the molecular clouds that fuel this ongoing creation. They are immense, cold, and opaque, absorbing visible light and forming the dark lanes we see cutting across the bright band of the Milky Way. Inside these clouds, where temperatures drop to just a few tens of degrees above absolute zero, Hydrogen molecules drift lazily until some disturbance, perhaps the shock wave from a nearby supernova, sets collapse in motion. From that moment onward, gravity takes over, guiding the gas toward the birth of new stars. Each generation of stars alters its environment, shaping the conditions for the next. The radiation from young, massive stars can both destroy and create, dispersing clouds in some places while compressing them in others. Over billions of years, this feedback sculpts the structure of the entire disk. The Milky Way's spiral arms are therefore not merely geometric patterns, but living ecosystems, continuously interacting with the forces that sustain them. Viewed from above, the disk resembles a great whirlpool, its spiral arms shining with the light of billions of suns. The interarm regions, though fainter, are filled with older stars and diffuse gas. This balance between light and shadow, between the crowded arms and the quieter gaps, gives the Milky Way its rhythm. The galaxy is a song of alternation, brightness and rest, creation and stillness, birth and decay. In the midst of all this, our sun travels quietly, orbiting the galactic center once every 230 million years. It moves through the spiral pattern like a leaf floating on a river, alternately passing through regions of density and calm. Each journey around the galaxy carries the Earth and its inhabitants through different neighborhoods of stars, each with its own history and flavor of light. The sky we see is not a fixed panorama, but a slow-moving panorama of cosmic evolution. Even the dust that obscures parts of the Milky Way is vital to its beauty. Those dark patches that blot the star fields are not voids, but concentrations of potential, places where new stars are gathering strength. Without dust, there would be no planets, no life, no reflection of light to sculpt the galaxy's features. The darkness in the Milky Way is as essential as the light. Together they define its form and give it meaning. The molecular ring near the center, the spiral arms stretching outward, and the halo beyond all work together as one vast mechanism. Gas flows inward, forms stars, and returns to the halo. Gravity sculpts the pathways of that flow, and time keeps the rhythm. The Milky Way is both a system and a story, an ongoing narrative of balance written in motion and light. Every part of it, from the dense clouds near the core to the thin outskirts where stars drift alone, participates in the same endless act of becoming. When we look up at the night sky and see that pale arc stretching from horizon to horizon, we are witnessing the cross-section of this great process. Every faint shimmer, every subtle glow, is a piece of a larger pattern that has been unfolding for more than 13 billion years. The Milky Way is not something that happened long ago. It is something happening now, in this very moment, across a scale too vast for our senses, but not beyond our understanding. Beyond the faintest glow of the Milky Way's outer halo, the stars begin to thin into loneliness. Their light grows sparse, the distances between them stretching into gulfs so vast that even light takes millennia to cross from one to the next. Out here, the galaxy fades not with a line or a border, but with a sigh, a gradual dissolving into quiet. The starlight, once thick and bright across the spiral arms, scatters until it becomes a whisper. The airless void holds that whisper, letting it travel forever without resistance, a soft echo of everything that has ever burned within the Milky Way's heart. This region, where the halo merges with intergalactic space, is not truly empty. It hums with particles too faint for eyes to see, atoms of hydrogen drifting like forgotten notes in a song that never ends. Every cubic meter of this silence holds a few lonely atoms, remnants of ancient explosions, wandering without destination. The temperature here falls close to absolute zero, and yet, even in this near void, the galaxy's gravity still lingers, faint but patient, holding its influence across unimaginable distances. In the far darkness, globular clusters move like slow lanterns, circling the Milky Way's core on immense elliptical orbits. Each cluster contains hundreds of thousands of stars bound together by mutual gravity, their light weaving thin, ghostly threads through the night. They are the galaxy's memories, relics of a time before the spiral arms had fully formed, fragments of the earliest order amid the chaos of creation. From a distance, they would look like suspended jewels, each one pulsing faintly against the black. The halo, once thought to be an empty region, is now understood as a great, unseen sphere, a vast ocean of dark matter, gas, and ancient stars. Dark matter gives it shape, invisible, silent, and unreflective, yet more massive than all the shining matter within the spiral combined. It surrounds the Milky Way like a hidden skeleton, a framework upon which light and life are draped. Without it, the galaxy's outer stars would drift away into space. With it, the spiral holds together, stable, enduring, quietly turning through the ages. Even in this distant place, motion never stops. Streams of stars, the remnants of smaller galaxies consumed by the Milky Way, drift through the halo like slow rivers. Their paths wrap around the galaxy, each one a thread in an enormous tapestry of memory. Astronomers trace these streams with patient eyes, mapping the Milky Way's past through the arcs of these lost systems. They are the fossils of cosmic cannibalism, reminders that the galaxy grew not by stillness, but by endless merging and renewal. Among these streams, the Sagittarius dwarf galaxy is one of the most visible victims of this quiet hunger. It is being torn apart as you read these words, its stars pulled into long, delicate trails that wrap around our galaxy's outskirts. Each star in that stream was once part of another home, another family of light, now folded into ours. In this way, the Milky Way expands, not through conquest, but through inheritance, adding the stories of smaller galaxies into its own. The halo breathes, not in the way lungs breathe, but through the slow exchange of matter. Hot gas rises from the galactic disk, thrown upward by supernova explosions, spreading into the outer reaches before cooling and falling back again as invisible rain. This circulation, called the galactic fountain, is how the Milky Way sustains itself, a cosmic respiration that has continued for billions of years. The gas that once burned in one generation of stars becomes the cradle for another. Sometimes, massive stars at the galaxy's edge explode with such violence that they send their remnants beyond the halo entirely, into the deep intergalactic medium. These expelled atoms drift for eons, perhaps never to return. And yet, they remain part of the Milky Way's essence, ambassadors of its past, carrying its elements into the wider universe. If you could drift out past the halo and turn back, you would see the Milky Way as a luminous whirl suspended in infinity. From this vantage, The galaxy would appear as a soft spiral of pale gold and blue, its arms curling gracefully around a radiant heart. Dust lanes would streak across the disk like brushstrokes of shadow. The faint halo would glow faintly, almost imperceptibly, a transparent sphere surrounding the central brilliance. Beyond that, nothing but darkness punctured by the distant shimmer of other galaxies. In that view, the Milky Way would look fragile, almost small, one among billions of galaxies scattered across the observable universe. Yet each one of those galaxies is as rich and complex as ours, containing its own billions of stars, planets, clouds, and histories. The vastness of the cosmos turns the idea of scale into something almost meaningless. Our galaxy, though immense, is but a single cell in a living, breathing universe. If you could drift in that space between the Milky Way and Andromeda, you would see a sight beyond imagination. Ahead, the Milky Way spiral would glow in soft bands of gold and silver, its arms curling like luminous rivers around a bright, dense core. Behind you, Andromeda would loom vast and bluish, its arms more open, its light cooler and more serene. Between the two, the dark would shimmer faintly with hydrogen gas, starlight, and the invisible pulse of dark matter. The silence there would not be empty. It would feel alive, humming with the slow music of gravity. In that dark corridor, rogue stars travel, solitary wanderers expelled by gravitational tides, moving between the galaxies like sparks between waves. Some of them come from the Milky Way, some from Andromeda, some from smaller galaxies caught between the two. Their journeys last longer than the lifespan of any star that ever watched them depart. Each one carries the history of its origin in its spectrum, the chemical fingerprints of long-dead suns, the ashes of ancient supernovae. They are not lost. They are messengers, moving through a bridge of time and space that few will ever see. As the galaxies draw closer, they begin to distort each other's shapes. The outer arms of the Milky Way start to twist, their elegant spirals bending slightly inward. Andromeda responds in kind, its structure warping as tidal forces pass through it like waves through water. These distortions are delicate and gradual, stretching over millions of years, but their beauty is unmatched, the universe performing a slow ballet in the darkness. At this stage, if one could look at the two galaxies from far above, they would appear as two luminous whirlpools drifting nearer, their arms reaching out like tendrils yearning for contact. Streams of stars begin to extend from their edges, forming long tails that glow faintly in the black. These are tidal tails, rivers of starlight drawn out by gravitational forces, connecting the galaxies like luminous bridges. Within those rivers, stars move in chaotic paths, some destined to be flung into intergalactic space forever, others pulled inward into the newborn heart of a merged future galaxy. Andromeda itself is immense, larger than the Milky Way, with nearly twice as many stars. Its central bulge blazes with ancient suns, while its arms shimmer with clusters of young blue stars born from abundant gas. In its heart lies a supermassive black hole, more massive than the one at the Milky Way's center. When the galaxies finally meet, those two black holes will begin their own intimate dance, orbiting each other in tightening spirals for eons until they merge, sending ripples of gravitational energy across the universe, silent waves that will pass through everything, even through you, without notice. But that moment is still far away. For now, the galaxies move slowly, drawn together by invisible threads. Between them, smaller galaxies and streams of matter drift like witnesses. The Triangulum galaxy, smaller than both but bright and restless, orbits nearby, its own gravity caught in the web between the two giants. It may join the merger or remain on the periphery, circling the edges of what will someday be a single colossal system. The night sky of the distant future will reflect this approach. Millions of years from now, Andromeda will no longer appear as a faint smudge, but as a distinct oval of light, brighter than the moon and stretching across much of the sky. The stars within it will become visible as separate points, and its spiral arms will glow with faint blue light. The constellations we know today will dissolve, their patterns rewritten by the motion of the heavens. New shapes will form, new myths waiting for new eyes to name them. As the galaxies near collision, vast clouds of gas will compress, igniting waves of star formation. Entire regions will flare to life with newborn suns. For a time, the combined system will shine brighter than it ever has before. Nebulae will bloom like luminous flowers. Clusters will sparkle like jewels scattered on velvet. Yet, amid all this creation, many older stars will drift into the deep outskirts, carried away by the merging gravitational fields. The boundaries between what was once Milky Way and what was once Andromeda will blur until no distinction remains. This is not destruction. It is renewal on a galactic scale. The same physics that pulls them together ensures that their stars will rarely collide. The distances between individual suns are so vast that even in a merger of billions, they pass by each other like ghosts. The drama happens not in impacts, but in gravity, the reshaping of orbits, the blending of trajectories, the creation of new order from old. Eventually, the galaxies will pass through each other and separate again, stretched and distorted but still intact. Then, gravity will pull them back for another encounter. This back and forth will repeat several times, each pass drawing them closer, until they finally coalesce into one. The process will take billions of years, yet to the universe, it will be no more than a sigh. When the merger is complete, the Milky Way and Andromeda will become one, a vast elliptical galaxy glowing with the light of trillions of stars. The spirals will vanish, replaced by smooth halos of light. The galaxy's core will blaze with energy from the merging black holes, while its outer regions drift quietly in long, stable orbits. This new system will shine for countless eons, a monument to the beauty of cosmic evolution. From outside, looking back, the galaxy would appear immense and oval, surrounded by a halo that stretches for hundreds of thousands of light years. Within that halo, countless smaller systems orbit, the dwarf galaxies, the stellar streams, the remnants of long-forgotten collisions. Some of these are only temporary companions, destined to fall inward and vanish into the central light. Others will remain on wide, slow paths, circling like distant moons for all eternity. The space between these galaxies, though seemingly empty, hums with a faint energy, the echo of the cosmic web that holds everything together. Streams of dark matter thread through the local group, connecting it to neighboring clusters. Through these invisible filaments, matter flows like breath, feeding galaxies with the raw materials of new stars. The local group is not isolated. It is part of a living system, a heartbeat in the vast body of the cosmos. Over unimaginable spans of time, the group will continue to evolve. Some galaxies will merge, others will fade. The smaller dwarfs may be stripped of their stars, their gas consumed by the larger systems they orbit. Each interaction will leave subtle imprints, arcs of stars, faint bridges of dust, gentle ripples of gravity, the handwriting of time written across the darkness. Eventually, the entire local group will coalesce into a single, enormous elliptical galaxy, a structure perhaps millions of light years across. It will shine like a lone lantern drifting in the cosmic night, surrounded by emptiness as the universe continues to expand. Every star that once belonged to the Milky Way, to Andromeda, to Triangulum, and to the countless dwarfs will find a new home within it. In the grand chronology of the cosmos, this will be the local group's final act. Unity through gravity, completion through merging. In the deepest sense, light is the universe remembering itself. It is the bridge between what has been and what will be. It carries the memory of stars long gone, of galaxies still forming, of life that arose and faded. And because it travels at the limit of speed, it defines time itself, the measure by which existence reveals its unfolding. Without light, there would be no history, no form, no awareness. With it, everything becomes connected. The journey of light is the journey of all things, endless, gentle, and full of quiet purpose. It leaves, it travels, it transforms, and it continues. Some of it reaches eyes, some becomes heat, some fades into silence, but none is ever lost. Each photon, no matter how small, carries a spark of eternity within it. When you gaze upward at night, you are not just looking at stars, you are looking into time. You are witnessing the universe in motion, every beam a thread in the fabric of its unfolding story. You are part of that fabric, woven from the same light that fills the cosmos. The starlight that brushes your face is the same starlight that shaped worlds, that forged atoms, that began everything. And it continues, flowing outward, forever, never ceasing. Light is the pulse of the cosmos. It beats through galaxies, through atoms, through hearts. It carries warmth and memory, birth and decay, distance and intimacy. It is everywhere, around you, within you, beyond you. It is the proof that nothing truly vanishes, that all things are connected, that time itself is an ocean of endless reflection. And as the light continues to travel, the universe continues to dream, quietly, endlessly, in radiance. And as the galaxies drift in silence, as light moves endlessly through time, as the stars whisper across the sky, the universe leans close, gentle and full of peace, and says, "Good night."